Hi, everybody. I'd love to introduce Jim Hall from Oxford University, where he is mapping the world's vulnerability to climate change so we can hopefully do something about it. Welcome, Jim.
Thanks very much indeed, Greg, for the invitation. So it's a great pleasure to be with you here. Thanks indeed very much for the invitation to speak here. I'm going to, if I can persuade my slides to go ahead, there we are, say a bit about the modeling and systems analysis within my group, looking at climate risk to infrastructure on very large scales, and hopefully show some things which are interesting and innovative from a methodological and data perspective, as well as showing some results which we think are quite important. And then I'm looking forward to feedback and some discussion when I'm done. I just put a few images up here to give some sense of the scope of what we're talking about. Impacts of climate change, so floods, droughts, storms, hurricanes, storm surges, wildfire, and the impacts that has both directly on infrastructure, and then the ways in which that can lead to wider business interruption and knock-on effects. So, for example, in the middle at the top here is the 2011 flood in Thailand, which, as many of you will be aware, resulted in a large chunk of the world's hard drive manufacturing, probably about a quarter of the world's hard drive manufacturing in Thailand at that time, and result significant impacts, for example, to Western Digital and to Toyota. And Toyota issued a profit warning, and their insurers were unaware or not completely aware at the time of the amount of exposure that Toyota actually had in Thailand to those floods when they occurred. So the business we're in is estimating the risks from these, and in particular the wider economic risks, and using that to inform investment decisions, adaptation decisions. Let me just rewind a little bit to give some sense of where risk modeling in this field has come from. Up until 1992, roughly, so the early 90s, insurance underwriting and reinsurance based on statistical estimates, so actuarial losses. And then Hurricane Andrew struck, and as you'll see in the quote there, it led to the insolvency of 11 insurance companies. And so around that time was when innovators were beginning to develop catastrophe models. I'll say a little bit more about cat models in a moment. And Hurricane Andrew really, because it was so surprising an event at the time, really kind of stimulated this transition within the industry from statistical and actuarial estimates through to much more model-based estimates with cat models. The interesting thing is to look at this time series after 1992. In 92, Hurricane Andrew looked like an extraordinarily large event and large loss to the industry. As we roll the clock forwards, these losses are getting bigger and bigger and even more extraordinary. So if one Googles cat model, this is what you get. This is not what we're talking about, however. What we're talking about is a layered risk analysis, which is driven by statistical simulations of spatial extreme events, and I'll come back to that in a moment, why that is so important, which is superimposed on layers of asset exposure that is combined with functions to describe the vulnerability of the assets, And basically a statistical convolution is done of those two things in order to come up with a distribution of different exceedance probabilities. And that's a business which I say has been going on for a long time, but has been dominated by a small number of cat model vendors who license their products as more or less black boxes. There's been a bit of a movement in the industry around the so-called OASIS loss modeling framework, at least to open up some aspects of that process and enable insurers to plug in their own data sets within an open loss modeling framework. But even that, the issue with cat modeling, amongst other issues, is that it is focused in the largest insurance markets. So in these figures, you should look at the percentages of coverage. So the numbers above the bars, and you'll see that, for example, coverage in Africa and parts of Asia is very small. So the cat modeling tends to have been concentrated in the European and North American markets. What's more, there is massive concern now about the statistical estimates upon which these models are based not being valid because of the impacts of climate change, meaning that the hazards are non-stationary. The probability distributions of those hazards are changing through time because of the impacts of climate change. Insurers are not particularly worried about changes decades into the future. They typically issue policies on a year-to-year basis, but what they are worried about is changes that are taking place now that have changed that may have changed probability estimates so that they're using the wrong odds when they're estimating insurance prices. But when we do start looking into the future, and insurers may not be, at least underwriters and reinsurers may not be all that interested in this, the insurance investors are, but lots of people, of course, are interested in what will happen to these risks in the future. These projections of increased and decreased flood risk, a lot of the decrease is due to changes in snowmelt patterns in the Northern Hemisphere, means that snowmelt floods are going to go down in the future. But as you'll see from the speckling, there's quite a lot of disagreement amongst climate models in terms of what may happen into the future. So we need to use multiple climate models if we're going to look at what happens in the future. Which takes us to the platform that we've developed within our group and with a bunch of partners internationally. And this is focused on at both global and there are some national versions of this tool, estimating climate-related risks, in particular to infrastructure. And we're interested in infrastructure because it's such a pivotal aspect of adaptation decision-making. Once you've made an investment decision or a land use planning decision in relation to infrastructure, then that is practically irreversible and your assets are going to be at risk and at increasing risk going into the future. Often if you build a highway, for example, then there's real estate development and other developments take place along that highway. So infrastructure is fundamental for lock-in of climate-related exposure. And also it's super important because it's the basis for systemic risks. That if a piece of infrastructure fails, a power plant, a highway, a port fails, then there's a whole series of macroeconomic spillovers, which mean that it's not just the direct damage to the asset or the business interruption from that asset, but also all of the other knock-on effects which lead to very widespread economic losses and indeed social and societal losses. So what we're interested in is managing those climate risks going into the future, making the right choices about climate proofing new infrastructure and adapting existing infrastructure is a really important part of that. And the decision calculus, which is set out here, basically looks at what are the risks now, what might those risks be in the future, how much could we get the risk down with for an investment in adaptation options, and so how does the risk reduction compare with the cost of adaptation option to enable us to prioritize. And as I say, we've developed a bunch of tools and interfaces to do that, both the GStrat interface and then the OpenJira toolset, which you can see there, which enables us to speed up a lot of these quite time-consuming and clunky data processing steps. But as I'll come to at the end of this presentation, there's a lot more to do in terms of making this workflow more efficient and scalable, and I'd love to chat more about that. Now let me just dive into two versions of this analysis. So to look at two combinations of hazards and infrastructure networks to give you a bit of a snapshot of some of what we've done at a global scale. As I say, we've done more detailed versions of this analysis and the adaptation decision-making at national scales, but I don't want to talk too long today to allow some time for some discussion and questions. So I'm just going to focus on two instances of global scale analysis. And the first is looking at cyclone risks to power infrastructure. This is a plot of observed cyclone tracks. It's great actually that we have this IB tracks database, which enables us to track cyclones. And what we then use is a synthetic version of that cyclone tracks data set to create lots of more versions of storm tracks in the future. And we combine that with a global analysis of power network exposure. So we and I'll go into a little bit more detail about how we go about synthesizing power networks globally. We then superimpose the maximum wind speed from the storm field, apply some downscaling factors, and then look at how many assets might fail for a given failure threshold, and so what the overall footprint of the cyclone track passing is. In order to build up this global power network layer, we developed with the World Bank a tool called Grid Finder, which combines global data sets on power plants. We're using a data set from WRI, but there are a number of different private and public power plant data sets out there. And Grid Finder basically uses a variety of different pieces of information, in particular nightlight data, which I'll say a little bit more about in a moment, to identify the most likely locations for high and medium voltage power networks. And there's some papers validating Grid Finder, and it performs pretty well. It's about the best we've got if we want global power network coverage. Then what we the Grid Finder gives us the power network exposure, so where the power networks are. There's a question, a big question around, well, what wind speeds do pylons and poles actually fail, and how does that threshold wind speed vary around the world? So the piece of work we've done to do that has been to look at nighttime light data before and after cyclones, hurricanes, and to calibrate that wind speed threshold in order to best fit the observed night light response. So to estimate, using our model to estimate where the nighttime light failures, the power failures would occur, and then to calibrate the model based on the wind speed threshold to give the best fit between the model and the night light observations. That kind of set up
your methodology. The physical attributes of the power grid seem to be rather important. I'm thinking some power lines are buried underground at a high expense. Some are on concrete poles, some are on wooden poles. The distribution versus transmission lines probably use different, strength. Do you have any idea how these things were built, or is it all hidden from you?
Yeah, no, we have, at least globally, we have no information about that. So this is what we're trying to calibrate, is to fit based on observations what the sensitivity of those networks are.
Okay. You're thinking of it as the generic network, or maybe a continental like specificity network. That's probably all you're going to get right now.
Yeah. Now there's this. What we're talking about here is an instance of a very general problem. Is that we can, and we'll come to this at the end, that we've got this abundance of data and a capacity to do very cool things, but then also some critical missing pieces. And what you've described in terms of the engineering of these assets, whether the poles are wood or steel, or whether the pylons are lattice or more novel designs, and what the condition of them, what the maintenance of them is, that is the missing link. And what we're going to talk fill that missing link. For the time being, we're calibrating, and the bottom left panel here shows some calibration. So in terms of wind speed thresholds, shows a bit about how this varies in high density, low density, and rural areas. And we've looked at high, medium, and low income countries. In fact, we can't detect much significant difference between medium and low income countries, but the high income countries clearly have a higher threshold in this analysis. So then what we do is we calibrate this based on the observed storms in the TRACS data set, the IB TRACS data set. There are a couple of then synthetic storm data sets, one from Nadia Blumenthal in the Netherlands, one from Ralph Toomey at Imperial College. And so we can, to do the risk analysis, we can run this large ensemble of synthetic storms, both representing present day conditions and future climate scenarios, in order to come up with these loss probability distributions. So here, the number of people impacted at different return periods. So that's one instance of some work. We haven't quite finished that off yet, but we're in the process of wrapping up another round of compute on that. You can imagine that to run tens of thousands of storms across a complex network like that is a moderately big compute job, but not devastatingly so. And then we'll be writing that up and publishing it.
So question on the storm tracks. I mean, it's rather hard to make a generator model for existing storm tracks, even harder to do it for various climate scenarios. So how do you, I guess, connect various climate scenarios to what they do to cyclones? Are climate models good enough for this? Are they fine enough resolution?
Yeah, no, that's a great question. So what is done with these climate condition versions is that so the future climate ones is that they look at the change factors in sets of parameters which describing the storm intensity and frequency and typically something relating to the shifts in the tropical cyclone belt. So you're not actually taking the storms themselves out of the climate models. You're using the climate models to give some sense in which the ways in which the statistics of storms are going to change in the future. You use those change factors in your statistical track model and generate a new set of tracks which somehow corresponds to the types of statistical changes which the climate models are predicting for the future. But that may still be wrong because we know that, as you say, that climate models are not great at that sort of thing.
Got it. No, that makes sense. Thank you.
Okay, so then the other example I just wanted to jump into is global transport networks. And this is something we've been working on for a while, probably 5 years ago now. We did a piece of work with the World Bank for a report which they published called Lifelines, which was, as far as we're aware, the first global analysis of the exposure of transport networks, not only to climate hazards, but in this one, we looked at geophysical hazards, so earthquakes and tsunami as well. And since then, we've continued working on this. And the piece I'm going to show here relates in particular to ports, where we've done a lot of work identifying ports worldwide, 1,350 ports. We've looked at using satellite imagery at the port assets and segmented all of those port assets. My PhD student did that by hand to identify where the breakwaters, the laydown areas, the quays, and crucially the landside transport connectivity, because that's often the most exposed aspect of a port, is do the roads or the railways leading to the port flooded. And then Jasper combined that with a new transport and trade shipping model, which was constructed with a combination of input-output data. So the imports and exports for different sectors at a country level, port bills and data which describe what commodities are going in and out of what ports, and then AIS ship tracking data, which is what we're looking at here. And AIS is an incredible data set. As you'll know, these are the 15-minute pings which ships send with their geolocation for safety reasons. But it's a vast data set. You can look at ships making their way across the planet. We didn't do that. We filtered it to specifically look at where they were going in and out of ports. You can see from these data sets really quite interesting data in terms of how long ports have been out of action for in these 4 different hurricanes and tropical cyclones, typhoons. So you can get a really kind of fascinating empirical picture of what the disruption from these types of disasters are. But we can also use this type of data to identify what ships are going in and out of what ports. And so basically built a port-to-port shipping network model, whose the observed disruptions from the grounding of the Ever Given container ship in the Suez Canal, and the way in which that Suez Canal blockage basically propagated through to trade disruptions all the way around the world, as in the days following that canal blockage. So what we've done in that analysis is looked at both the scale of climate and geophysical risks to different ports worldwide. So calculating both the estimates of the direct damages and estimates of the ports. And you can see how different ports are vulnerable to different hazards. The degree of that vulnerability, of course, is modulated by the way in which these ports are engineered. And we've actually, going back to the point around, do you know how power networks are engineered? Actually, we know a lot more about the ways in which ports are engineered compared to what we know about power networks. So you can imagine that there's a kind of trade-off here between some ports being incredibly valuable in terms of the assets there, but those ports, particularly if they're modern ports in advanced economies, also being very well protected against hazards. So you look, for example, at ports in Japan. Japan is exposed to pretty much everything in terms of climate disasters and physical hazards, but they're also very highly engineered ports, so they need to have exceptional events if they're going to get damaged. And what we've looked at, yep.
So it looks like the focus of the analysis is on specifically damage to ports. But one thing you mentioned is like the Suez Canal, the Panama Canal. There's a bunch of choke points as well as just routes. Like if a storm happens, maybe you can't drive through that, ocean for that week or whatever. Are you looking at all these things across the network, or is this analysis just the ports?
So this analysis is just ports. Mm-hmm. I know, yeah, exactly what you're talking about here. There's the Suez Canal, of course. There's tremendous analysis in the tremendous interest in the Straits of Taiwan at the moment. And so this Oxmar Trans shipping model does tell us what ships with some approximation of what commodities are going through any shipping route in the world. We haven't looked at that in much detail yet, besides the Ever Given in the Suez Canal. But yeah, we do have the data sets to do that.
Okay.
And what we're showing here is that we can, by using a fairly kind of approximate version of how economic activity is dependent upon maritime trade, you can see an expected loss. So these numbers might actually seem to be quite small, but it's because the events are really very rare. The losses are much bigger, but the expected losses are low. That we can calculate these losses of maritime trade on average each year, and some estimate of how that ripples through into economic activity on an annual basis, and some analysis of how that goes from port to port and from country to country, and looking at what these colored diagrams here show for different countries and for different sectors, how exposed those countries are in terms of potential consumption losses, potential industry output losses, and how that plays through in inputs and imports and exports. I'm coming to towards the end here, but there are a couple of interesting recent developments of this. One slight but interesting tangent is that we've teamed up with engineers in Oxford who are looking at decarbonisation of shipping, and in particular how you would do that with green ammonia, which is the most viable fuel for long distance shipping, any shipping over about 1,000 miles. You can't do that with batteries. You could do it with e-fuels, but it's a question of, but producing ammonia is much cheaper than producing e-fuels, so synthetic hydrocarbons. So this picture here shows our estimate of the green blobs here is where is the ammonia production cheapest for shipping, and the black lines are where is this ammonia going to be being shipped from the sites with very, very cheap solar energy. That's where you're going to be putting your electrolyzers to create hydrogen and drive batteries wash process, and then where you're going to be shipping it to. And Australia is going to be a vast producer of green hydrogen, green ammonia, and they'll be shipping a lot of that up into East Asia. West Africa will be shipping it up into Europe. Chile will be shipping it into North America. Though actually a subsequent analysis, by the way, was looking at hydrogen subsidies. And if you put the level of hydrogen subsidy which is coming into existence in the USA, then Chile gets driven out of this market. Those green blobs in Chile no longer exist. It's all going to be produced in the USA because of the subsidy level for hydrogen. A little bit of a diversion there, but an interesting one. And all of this is based, on the one hand, on a spatial optimization of the supply infrastructure, and then on the other hand, this port-to-port shipping model that we have. And another piece, just out of passing interest, that we're doing with the port-to-port shipping model is that we can route agricultural commodities through the shipping network. So we can see if you have a price shock in food, what countries are most exposed to those price shocks, and typically it's places which are very import dependent, and we're also illustrating that some parts of the world the costs of transport of agricultural commodities are really very high. And this is a piece of work in progress. We've got this work in review, and we're really interested in doing large scale risk analysis of global food commodities and bilateral trade. So just a kind of final thought, which I'd like to discuss, and you'll have got quite a big sense of this already, I'm sure, is that by pulling together all of this Earth observation, crowdsourcing, document scraping, we're now in really quite an extraordinary position to map and model these networks, approximate supply chains, estimate climate risks globally. But as your questions have already illustrated, there are some big gaps there. And a lot of this comes down to crucial pieces of evidence of the type that I've already been asked about. So asset condition, how strong are the pylons, activity intensity. So we can track the ships, we can get also, thanks to Google, some estimates of the traffic density. But for example, the amount of power going through power lines, the amount of water going through pipe networks, those kind of flow things, and also exactly what trucks are taking from where to where, and what inventories there are. So what stocks of food commodities, of fuel, of other inventories are. These are all things which are really difficult to access and make this modeling task still quite difficult. Validation in extreme events, we can observe damages from space, we can look at building damage, we can look at night lights. But in order to validate a complex model like this, you need kind of multi-dimensional data sets before and after the impact event, which kind of help you to pin down each causal link in the damage disruption chain, and building up that kind of validation data is problematic. And we're interested in not only what this looks like now, but ways in which it's going to change in the future. And we know that that is due to a whole series of processes of socioeconomic change, technological changes, political events, which are to some extent unpredictable. So projecting this type of analysis into the future, which the business we're in has fundamental limitations because of the deep uncertainties around what will happen in the future. And I hope that's given you some food for thought, and hopefully kicked us off with some questions for discussion. And I hope also that there might be some suggestions for what we might do about some of this.
Well, fantastic. Thank you very much. I know you have a few questions here. So I guess one question that came in is, everything you said so far has been more pointed kind of impacts, like you hit a port or something like that. What about things like, well, I'm thinking about, okay, so you have a cyclone hitting a region, but you don't have a drought affecting agriculture in, you know, a breadbasket region. How will that, like, how can you adapt your techniques to do like regional kinds of whole industry damages, not a single location damages?
Yeah, okay, so there are a couple of points to that. One is the spatial extent of the damage, and sometimes that can be, these impacts can be regional or global in perspective. I should have said a little bit more about that, because that's a really interesting problem. I mentioned our work on multiple breadbasket failures. So we are estimating the joint probabilities of events hitting multiple regions of the world at the same time. That is still a kind of really active and interesting research area, creating those multivariate spatial event sets. And this is, I think, a really interesting area for generative AI. We've got some work with GANs, creating many instances of realistic spatial structures of windstorm events is what we're working on at the moment. The issue is, as you'll know probably better than me, is these are data hungry methods, and we're interested in extremes. So you train them on a ton of data, but they're biased in the extremes usually, unless some people on the call have got better experience of this than I have. The second point you made was around compound effects. And I think that's super important because if we look, for example, at questions around what really hits, for example, poor countries, is when they're in some kind of distress state already. Maybe it's over-indebted countries getting hit by a natural disaster at the same time. And that puts them, they don't have the fiscal headroom to cope. Maybe they're going to default. A whole ton of stuff happens following from that. So this question around, in particular, how financial and economic risks intersect with natural hazards or maybe other aspects of hazard. It might be conflict or pandemics. In compound risks, I think is really important.
So let's do one compound risk, which seems it's going to be very common, is water plus drought. So I mean, I'm thinking of river systems, because if you have less water coming from the sky or from snow melt, I'm thinking California right now, which depending on the previous winter, you have very different irrigation scenarios. You have downstream effects, not even where the drought happened, but where the river system lets out. So I'm thinking as North America, if you have Midwestern droughts, New Orleans will have less water, which is very far away from the drought. So how do you incorporate other features such as river flow systems into such compound analysis risk analysis?
Yeah, well, that's in a sense that is one system or a series of neighboring systems of the same type.
Yeah.
And so you're absolutely right that if you're going to properly analyze drought risk, you need to have at least some approximation of the water balance. So where the water is being stored and where's it being transferred. This is what it infuriates me a lot about. There are many papers on drought risk published, and the vast majority use meteorological drought indicators, so some kind of precipitation deficit, for example, and that you can create a picture of a map of the world with precipitation deficit, which tells you where it's dry at the moment, but that doesn't account for the dynamics of storage and transfer. What matters from a drought perspective is water shortages. So people whose water needs are not being met, be that in urban areas or agricultural areas. In order to do that, you need to model the stocks as well as the flows.
Yeah. And how feasible is that? So what I'm thinking is we had two speakers here, one in California's water model, which is all crazy water rights, and Israeli water model, which is communal ownership and, it's essentially planned system. But I mean, they have their own models because they're very different system, but presumably every water basin in the country is going to have its own radically different way of managing water, which is going to affect the impact of floods, of droughts.
Yeah, no, I mean, there's some very cool data now on, so there's a data set of reservoir areas, a time series data set. So these are Earth orbiting satellites, so every fortnight you get a reservoir area, so you can approximate the reservoir volume changes from the changes in reservoir area. There are people, I've had a student trying to looking at the spatial correlation in that. So are the zones where these things vary more or less in a correlated way, which kind of suggests they're part of the same operational system. There's a US hydropower output data set. So we're trying to learn reservoir operation rules, again, machine learning, relating the reservoir areas with the hydropower production. These are invisible rules. Hydropower operators don't tell you what they're doing, but if you can learn them. So there are some interesting things going on in that kind of space.
No, that makes a lot of sense. So now moving from natural to like our responses, you have data on how, let's say the World Trade Network, I mean, especially for the ship data, you have fantastic idea where the ships are going and how they respond to a few localized changes. But mitigation is a much more drastic change. I'm thinking US is trying to divest from China into more manufacturing facilities across the world. So you can make within 5-10 years pretty radical changes to the trade network. How could you like get a handle on the possible alternative networks we might have?
Yeah. So we've used a OECD trade model, which has some versions of future trade. In fact, it's an OECD shipping model. And an interesting kind of version of radical change in the future is if we're in a net zero world, then all of the coal, oil, and gas, which is getting shipped around at the moment, is no longer being shipped. And so there's a set of, this is basically driven by a global macroeconomic model with different scenarios. And in the net zero scenario, there's none of that trade going on, and that the OECD then kind of give you a version of the imports and exports from all the worldwide countries, so you can create a map which looks really different to what it looks like now in terms of what the shipping network is going to do. Another thing, I showed you just in passing this this food shock model, and one of the big issues in relation to food shocks is food export bans. We have that. We've had it in Russia in 2011. Recently, there was an export ban in India. So you can impose an export ban, take that out of the trade model, and look at the price adjustment that you get in the global food commodity price if a big exporter is no longer exporting. Of course, what happened in Ukraine as well is another instance of that. So you can do scenarios of that type.
So let's go into scenarios, because some of these are really interesting. The decarbonization one, so you have ammonia, methane would be another transportable thing, hydrogen, tricky but doable. And if you start pulling out coal, there's a new network of transportation that's required. Because as you said, I mean, I guess there's a few things. How do you infer the new network? And you've already done some of it. And how do you schedule the deployment of the network? Because I'm assuming you can't start using ammonia ships until at least several ports along the ship's path will have ammonia refueling facilities. So you have to bootstrap that system, but it's a globally coordinated bootstrap. So how can you use your tools?
Right? Yeah. No, that's a problem we're working on at the moment. I mean, the first movers in this are around green corridors. So there's a Rotterdam, Singapore Green Corridor project, and so that involves kind of putting in enough ammonia infrastructure and having enough ship owners, and there are ship owners in the world. We speak to some of them who are already commissioning ammonia fueled ships. Mm-hmm. So you're right, there's a coordination problem, but actually what the first movers do isn't all that sensitive to the endpoint, because the endpoint is going to be so big and so different. The first move is almost certainly consistent with it.
Well, I guess what I'm thinking of here is if the IMO wants to, I don't know if it has that much power, wants to plan out the deployment of this network and push it forward by 10 years compared to the natural capitalistic version, is it feasible to start saying these 5 ports are the linchpins, install, refueling facilities there, and then every, let's say 80% of ships in a Pacific route will catch one of these ports in their cycle?
Yeah, and that effectively in this optimization of the bunkering locations is what we've done pretty much. is
Okay.
where are these key bunkering locations relative to where the hydrogen and ammonia is going to be produced.
Got it. And the clean stuff is going to happen where you have solar, because you have the raw materials are everywhere, but the power for them is what's scarce,
Yeah,
right?
yeah. Now this is driven by large areas of reliable solar. Those are the blobs which show up on the map.
Okay. And then the models you're using are primarily, I think it seems like network models or kind of point impact models. But it seems like a lot of the tasks you're describing are more of the required queuing behavior. This happens at this rate, that thing happens at that rate, or at the worst case, agent-based models where really everybody's pushing each other to the fine granularity. So what's a sweet spot of, what kind of model will answer a lot of these questions of the dynamics?
Yeah. So what are the categories of model we're doing? And I kind of digressed a little bit at the end onto the future of shipping problem, which is basically a spatial optimization problem, and we do quite a lot of those spatial optimization problems. Back to where I started with the climate risk analysis. These are, as you will have seen, event-based models. So they're based on doing simulations of very large numbers of events with relatively simple sets of functions downstream from the event occurring. Right. So we're not in the business of doing very kind of complex agent-based dynamics in this thing. In some senses, I mean, is it an agent-based model? Is it a network model? Tomato. But these aren't desperately complex dynamical things. They're big, they cover a large area, they have lots of data in them, and you have to do lots of simulations. But what's actually embedded in each one is not a particularly big deal.
Okay, and now the reason I'm going there is because if I am a company that wants to do something based on your insights, now I'm not UN right now, I am like a Ford or somebody who has a supply chain. Now I do have maybe an agent-based model that has to be kind of parameterized by the events and the dynamics of everybody else in the world, which has to be far coarser, but I have a decent model of myself. So I guess how would you see your work being adapted to a particular decision maker, changing their value chain?
Yeah, no, that's a really interesting question, and we have had a look at some large firms' supply chain data. Mm-hmm. On the whole, these they look at the world in a slightly different way, in the sense that if you're, I don't know, a consumer food manufacturer, you have a set of different products, and then you have a kind of hierarchy from each product, which goes down through supply chain tiers to your different tiers of suppliers. And sorry, that's true. Tautology, isn't it? But you know what I mean. Whereas, for some of those things, you may have good geolocated information if you're worried about the environmental impact and the biodiversity impact of your farmers. Then you might have put quite a bit of effort into geolocating where those farmers are. For other things, actually, firms really struggle. They maybe know the name of their supplier and have the head office, but actually where the manufacturing is taking place, they may be completely unaware. But that's still, if you plot all of that out as a kind of network globally, it's still a very partial subset of all of the trade flows going on in all of those different economic sectors. The journey we're on is to try and kind of come up with maybe a less complete, in terms of categorization, but more spatially and economically complete version of these various flows across the globe.
That makes a lot of sense. And now, in terms of so you mentioned a bunch of applications of optimization and AI, like generative models for storm tracks and optimization of various designs. I guess, where do you see like machine learning research contributing to this line of work?
Yeah. So in lots of ways, certainly so I'll probably miss some out here because there's so many of them, but in terms of the whole kind of asset recognition or recognition of what's going on the ground, some of this is computer vision or other forms of categorization problem. So kind of creating these data layers that we depend upon from a variety of different data sources geospatially, that's a big chunk of stuff. As you say, there's the generative bit in terms of creating the extreme event sets. There's a whole kind of set of different types of learning relationships, and I gave the reservoir area hydropower production instance. So there are cases in which we can empirically learn physical relationships which are not accessible to us. Yeah, no, let me leave it there. Can you think of any others?
Oh God. Probably better optimization. I think part of what I went in for individual actors, they would probably want reinforcement learning or some kind of a dynamic. I respond like this whenever this crazy thing happens. For you have an extensive library of crazy things happening.
Mm-hmm. Right. Yeah. And that, I mean, you mentioned the upstream downstream water situation, and sometimes that is transboundary, so you have actors in conflict with one another, and that potentially leads itself to a reinforcement learning type scenario.
Yeah, and I'm thinking also, if you want to engineer an economy or engineer a transition, you want roughly a model of this scale, but probably even more granular, right? When you want to say which ports you want to transition, there is a big optimization thing and just a macroeconomic model in there, and it takes a lot of compute at that point when you have so many models interacting.
Yeah, right. I mean, there's some very kind of well-known optimization problems. You can imagine that in the whole kind of transport network disruption thing, there are tons of rerouting calculations one needs to do out of a network. Then you have to reroute everything else around that. That's important because it determines the transport delays, the losses of perishable goods, the wider supply chain disruption.
Yeah, and to what extent rail is a substitute for ship and air, depending on what you need. Like, I guess actually the Suez Canal, a bunch of companies booked up all the air cargo capacity, as you know, when it turns out they it's going to perish.
Yeah, and so those adaptive behaviors during after a shock are really tricky as well. I mean, some economic modelers there's a chunk of business around doing general equilibrium models of these types of problems, but on the whole, in these scenarios, often prices are quite inelastic. People adopt heuristics rather than this being anything near an economic equilibrium setting. Sometimes, I mean, there are price adjustments. You get price hikes of materials when you're reconstructing after a disaster. That's an equilibrium effect. But there are lots of things going on which are far from equilibrium.
Yeah, and certainly in the first the single-digit year granularity, yeah, it's all heuristics of how some warehouse manager runs their warehouse.
Right. Yeah, and so that kind of stuff is really quite invisible. There's some people have done surveys, so they've gone to ask these questions, and that's really that's gold dust, that kind of data.
Yeah, at best you can, if you're working with one company who knows what their supply chain looks like, which is a problem, then you can start asking, what would you do in this scenario? Or they can decide what to do and propagate this down and hope the suppliers listen, which is also a question.
Yeah.
Well, that makes a lot of sense. Maybe, wow. One, you were maybe last question. You were saying compute is a challenge. I mean, so what scale of compute are you running up against?
So we're running on a cluster with some kind of hundreds of cores in this department, and we use the university's advanced research compute facility. So this is, as I say, it's not extraordinary compute in any sense, but it's not small either.
Right, that makes sense. I guess if there's any part of this purpose, if there's anybody in the call who might be able to help, this is a matter of it sounds like a classic cloud computing kind of challenge where it costs money, but it's that kind of compute infrastructure exists. It's plenty.
Exactly. I mean, if you ask me what would make your dreams come true, it wouldn't be compute, wouldn't be top of my list.
Mm-hmm. Okay, well, that makes sense. Well, thank you very much. It was fascinating.
My pleasure.